right, here we go with Chapter 2. Chapter 2 is going to cover our basic chemistry. In this chapter, we're going to cover the chemical elements, molecules and compounds, chemistry of water, and acids and bases. But we're going to start off by talking about the search for life on Mars. Specifically, what we want to know about life on Mars is whether or not Mars ever have the conditions that could potentially support life. So take a moment and think about what sort of conditions would we be looking for on the planet of Mars. So if we want to know if life was ever possible there, what sort of things would we look for? Well, I'm going to tell you. So the rover Curiosity, it looks for elements that are going to be associated with life on Earth. We use the ChemCam that's going to use a laser to blast rocks apart, trying to look for water, because as we know it, life on Earth is not possible without water. So if we're going to find life on another planet in a form that we are able to identify as life, it's probably going to require water, because that's what we know of life. So the ChemCam used a laser to blast rocks apart to detect water, and then another instrument on board used mass spectrometry to look for carbon, hydrogen, oxygen, and nitrogen in the soil. Any particular reason why we would be looking for carbon, hydrogen, oxygen, and nitrogen? It is because those are the components that all living things are made up of. So here we're going to take just a moment to look at the composition of the Earth's crust and its organisms. Here is just a comparison of the elements that make up the Earth's crust and living organism. And the graph inset shows that the Earth's crust primarily contains elements of silicon, aluminum, oxygen. Living organisms, on the other hand, things like trees and humans, they're going to primarily contain elements like oxygen, nitrogen, carbon, hydrogen. Biological molecules also often contain the elements sulfur and phosphorus. Almost everything on Earth, well, not everything on Earth is going to be comprised of matter. The air we breathe, the water we drink, anything that takes up space and has mass is what's known as matter. All matter exists in one of four states: solid, liquid, gas, or plasma. And all matter, both living and non-living, is going to be composed of basic substances called elements. So we're going to talk about elements. Elements are going to be substances that cannot be broken down into a simpler substance by ordinary chemical means, meaning they're only going to be composed of one type of atom. Each element has its unique chemical characteristics, or its unique chemical properties, such as density, solubility, melting point, reactivity. There are 92 elements that are naturally occurring. However, only 6 elements make up 90% of the body weight of organisms. You can remember these with the acronym CHOMPS. I know, it's not great, but CHOMPS. Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These are going to be what make up 95% of all living things. And the properties of these elements are absolutely essential to the unique functions of cells and their organisms. So we're going to start off by talking about atoms. Atoms were discovered by John Dalton. He was a 19th century English scientist. He developed what we know today as the atomic theory. This states that all elements are made up of tiny particles known as atoms. Atom is from the Greek, meaning uncut or indivisible. I will frequently give you Greek root definitions. I will never ask you to memorize that. I don't ever ask you to know what the Greek root is of anything. I provide it because I think it helps me learn what words are if I know what those words mean. So it helps me learn. I'm going to share it with you. I'm not going to ask you to memorize it, but if it helps you learn, great. The atom is Greek, meaning uncut or indivisible. An atom is going to be the smallest part of an element that displays the property of the element. So for example, whether you have a brick of gold or a single atom of gold, it's going to react in the exact same way all the time. It's going to melt at the same temperature. It's going to solidify at the same temperature. It's going to react to the air around it. It's always going to react in the exact same way every single time if it's pure gold. Same with oxygen. whether you have a small amount of pure oxygen or a large amount of pure oxygen. Oxygen is always going to behave the exact same way every single time. So an atom is going to be the smallest part of an element that displays the property of that element. An element and its atoms share the same name and is annotated with a 1 or 2 letter symbol that stands for its name. So for example, helium over here is represented by the letters He. Carbon is going to be represented by the letter C. N is going to be used for nitrogen, O for oxygen, so on and so forth. So the element and the atom share its name, and it's going to be annotated by a 1 or 2 letter symbol that stands for the name. This is not considered an abbreviation. You do not need to put a period after the C if you're annotating carbon, because it's not considered an abbreviation, merely a symbol. Oh, pardon me, I've got hiccups. So all atoms are going to be composed of several subatomic particles. The most common of those subatomic particles, and really the only ones we're going to discuss in this class, are going to be protons, neutrons, and electrons. And I do want you to know some of these characteristics, so we're going to talk about each one of these. We're going to start off by talking about protons. Protons are going to be found within the central nucleus. They're going to be positively charged, and they're going to have 1 atomic mass unit. So the particle proton is going to have a positive +1 charge. It's going to have a mass of 1 and be located in the nucleus. Neutrons, on the other hand, are also located in the nucleus. However, they do not have an electrical charge. So they are neutrally charged. Protons are positively charged. Neutrons are neutrally charged. No charge at all. They are also going to have an atomic mass of 1 and be located in the nucleus. Electrons are going to be our next subatomic particle. Electrons are going to be have an electric charge of -1, an atomic mass unit of 0, and they're going to be found not in the nucleus, but actually orbiting around the nucleus in what is known as an electron shell. We're going to spend a lot of time looking at electron shell. So here we go, here is our electron. It's going to be orbiting around on the outside. Electrons are negatively charged. They have a very, very low mass. It's not that they have no mass, because nothing has no mass, but their mass is so incredibly small that it's negligible. So we say it's 0 for the purposes of calculations. The precise location of the electrons is very difficult to establish, so they're often indicated using shading. Like the electron is not going to be located right here. They're constantly moving. They're whizzing around over and over and over again. So usually we just shade where they are, because at any given moment, it's kind of like, I don't know, it's kind of like the Flash. You know, this electron is moving so fast, it's just a blur. It's just a blurry halo effect around the central nucleus. So when using a model of an atom to predict chemical reaction, we indicate the average location of the electrons using those electron shells. It's important to note that unlike the drawing you see here, atoms are mostly empty space, just nothing there. So if an atom were to be drawn as the size of the football field, a nucleus would be roughly the size of a gumball in the center of the field, and the electrons would be like microscopic particles whizzing around in the upper stands. There is a huge amount of blank space between the nucleus and that first electron shell. So these models are only approximations of where electrons might be found. But the reason we draw them this way is because if we were to draw them accurately or to scale, that there wouldn't be enough space. This electron shell would be so huge and the nucleus would be so incredibly small that it just would defeat the purpose of being able to draw it at all. So we use approximations and models when showing the structure of atoms. Next, we're going to talk about atomic number and mass number. Each element is going to be represented by 1 or 2 letters that give it its unique symbol, as we said before. So in the case of carbon, the atomic symbol is going to be the letter C. The atomic number, on the other hand, is going to be is equal to the number of protons in each atom of an element. All atoms of the same element have the same number of protons in the nucleus. This is what gives the element its unique properties, the number of protons. If you change the number of protons inside of an atom of carbon, you no longer have carbon. So for example, if this was, well, this is helium right here. If we were to take one of those protons away, we wouldn't have helium anymore. We would suddenly have a completely different element known as hydrogen. If we were to add another proton, so we have 2 protons in here, if we were to add another proton, we wouldn't have helium anymore. We would suddenly have lithium. Lithium has 3 protons in its nucleus. So the atomic number is going to be responsible for the unique properties of that atom. And generally, atoms are considered to be electrically neutral, meaning that there are going to be equal numbers of protons as electrons. So if there are, in the case of carbon, the atomic number is 6, that means there are 6 protons in the nucleus. That means since protons are what? They are positively charged. That means we have 6 positive charges in the nucleus. If this is going to be electrically neutral, meaning that the overall charge is 0, we must have 6 negative charges to balance out the 6 positive charges. So if we have 6 protons in the center, we must have 6 electrons buzzing around on the outside to help balance that atom. So neutral atoms have an equal number of protons and electrons. The mass number, on the other hand, is kind of like the atomic number, only instead of just looking at the number of protons, it also includes the number of neutrons. The mass number of an atom is equal to the sum of the number of protons and the sum of the neutrons in the atom's nucleus. Typically, when we're looking at an atomic symbol, the atomic number is going to be written as a subscript to the lower left of the atomic symbol, and the mass number is written as a superscript in the upper left of that atomic symbol up here. So there can be variations. Like I said, if we were to change the structure of an atom, so if we were to change the number of protons, we would see that we have completely changed the atom itself. All of its properties changed. However, there are such a thing as isotopes, where we can change the atomic mass of an atom without actually changing a lot of its properties. So this would be what's known as an isotope. Isotopes are going to be atoms of the same element that differ in the number of neutrons. Therefore, they have different atomic masses. Carbon-12 has 6 protons and neutrons, and it has 12 protons and neutrons, 6 of which are specifically protons. So if we have an atomic mass of 12, an atomic number of 6, that means we have 12 protons and neutrons, 6 of which are protons. That must mean the remaining 6 are neutrons. Carbon-13, on the other hand, has an atomic mass of 13, an atomic number still of 6. If that atomic number changes at any point, we no longer have carbon, we suddenly have nitrogen or oxygen. But if we have an atomic mass of 13, minus the 6 protons, we must have 7 neutrons in carbon-13. Carbon-14 again has only 6 protons, but we have 14 for our atomic mass. So we take our atomic mass minus our atomic number, and that gives us the remaining amount of neutrons found in that particular atom. The reason that we care about this is that isotopes can actually be incredibly useful to us. There are such a thing as many isotopes are not actually stable. So if we start adding a bunch of neutrons into the nucleus, we can destabilize that atom as a whole. And we can form what are known as radioactive isotopes. So some isotopes of an element are going to be unstable or radioactive, meaning that they're going to spontaneously decay because they are not stable. When they decay, they're going to give off energy in the form of rays and subatomic particles. So for example, carbon-14 will decay over time to become nitrogen-14, which is going to be the stable isotope of nitrogen. The radiation given off by radioactive isotopes can be detected a variety of ways and used to date objects from the past. And create images or trace the movement of substances throughout the body. Really low levels of radiation can be used to help image body tissues and organisms, or body tissues and organs to help us study what's going on inside the human body.